Hey guys, how's it going? Here's Mike coming at you with another video on discrete mathematics. In the previous video, we saw several sample proofs where we proved facts or theorems using methods of indirect proof, namely proof by contradiction or proof by the contrapositive. In this video, we're going to begin to talk about set theory, just going to talk about some basic properties of sets, some different types of sets that we commonly encounter in any work that we do with sets. So we've already had a little bit of an introduction into what these guys are from earlier on in the course. Recall that if we want to look at a group of objects, they could be numbers, they could be names, they could be words, they could really be whatever we want to look at. We can talk about and look at these and look at this group of objects using sets. The names for each of the guys in the set, each of those guys that are in there that are making up that whole group, those are called the elements of a set. That's something we didn't perhaps mention earlier on in the course, but each guy in that set is called an element of the set. And when it comes to writing sets, the order in which we write these elements does not matter. So here I have a quick sample here. If I was given the sets just with 1, 2, and 3, I could write it as 3, 1, 2, 2, 1, 3, 3, 2, 1, 2, 3, 1. I could write it all those different ways, and they would all be the same set. We're all talking about the same set. Also, note that when we write the elements in a set, we separate them with commas. And also, we're never going to repeat an element more than once. So if I said 3, 1, 2, 1, 3, well, we see that we have the 1 showing up twice, and we have the 3 showing up twice. We wouldn't write it like that. We would just write it as 3, 1, 2. We only write each distinct element of that set only once. Earlier on in the course, we talked about sets that were determined by a defining property or a predicate that the element had to satisfy. We saw cases where, say, x was an integer that made 2x less than 5, or something like that. So we've seen some of those kinds of guys. For the most part, when we're talking about things in the math world, those are the kind of sets that we are working with. The set of all x values that satisfy maybe some equation or some inequality, or we work with our common domains, the set of all natural numbers, the set of all integers, set of all rational numbers, or the set of all real numbers. So what we're going to focus on in this video and the next couple of videos is not how we get a set, but how sets work with each other and the relationships between sets. So suppose we have two sets, capital A and capital B, and those are typically common names that you'll see being used for sets. We say that A is a subset of B, and there's two other ways to say this. That is the same as saying A is contained in B, or B contains A. So those three things are saying the same thing. So we say A is a subset of B if and only if every element of A is also an element of B. So if you take a look at your set A and your set B, If every guy that's in set A also lies inside of set B, then we know that A is a subset of B. And we have a special symbol for this. We have A, and then it looks like a lowercase c, and underneath it is one horizontal line. Looks roughly like that. And this says that A is a subset of B. A can be equal to B, and it's the horizontal line there that gives us that option of A possibly being the same as the set B. Now, in terms of a quantified statement, how could we write this definition of A being a subset of B? Well, we'd say for all x in some domain capital D, but not really needed, just for all x, if x is in A, or if x is an element of A, then x is in B, or x is an element of B. So that's how we can write this definition of a subset as a quantified statement. Now, if we take the negative of this quantified statement right here, we would come up with the quantified form of saying that A is not a subset of B. So we know that when we take the negative of a quantified statement, the quantifier gets switched to its opposite, and then we take the negative of the statement form that follows the quantifier. So if you do that, you come up with the next definition. We say that A is not a subset of B, if and only if there is an element of A that is not an element of B. The symbol for that, for saying that something is not a subset of something else, well, we draw that same lowercase c and then a horizontal line underneath it, but then we put a slash through it. And the quantified statement form of saying A is not a subset of B is that there exists an x such that x is in A and x is not in B. Now, this notation here, as we just said, this includes the possibility that A is equal to B. It includes the possibility that A and B are the same set. We have a related yet separate term for when A is a subset of B and A and B are not the same. We call A proper subset of B. So we say A is a proper subset of B if every element of A is in B, but there is at least one element of B that is not in A. Very shortly, we'll get a more visual representation of this, and we'll see a way to help us make more sense of that. But we do have a related symbol for showing a proper subset to write that something is a proper subset of something else. We would say this. We have that same lowercase c, but we don't put that horizontal line underneath it. So if you don't see that horizontal line, then you know that it's a proper subset. If you do see that horizontal line there, then these sets could be the same thing. Okay, so something I just want to talk about pretty quickly here. Sometimes folks misuse the subset notation and the elements notation when it comes to writing something as a subset of a given set, or saying that something is an element of a particular set. As we said, when you have a set written out, the guys written in the middle of the commas those are the elements of the set. If you want to say that something is an element of a set, then you're just going to take that one guy. It could be a word, it could be a number, it could be a shape, whatever, but you're just going to take that one guy and you're not going to put it inside of the squiggly brackets. You're not going to put it inside of the set brackets. So if you just want to say that some number is an element of a set, then you would just take that guy, that number, that word, whatever, write this symbol there, as you see, and then you would write your full set, 1, 2, 3, 4. If you want to say that some particular element is a subset, or something is a subset, you're going to take one or more elements of that set. You separate them by commas if you're taking more than one, and you put the set brackets on them. And you enclose all those guys, which are separated by commas, inside of set brackets. When you have set brackets on it, then you put the subset symbol. You put this guy right there. If your object or group of objects does have the set brackets on them, you are not going to use the element symbol. That's the first incorrect use of the notation here. So if you have set brackets on things, it's not an element of it. I'm going to put a star next to that because later on we're going to come to a special set where something with a set bracket is actually an element of a set. But for our purposes right now, at this stage of the game, if a thing or several things have set brackets on them, it's a subset. If you're just talking about one guy and there's no set brackets on them, then it is an element of that set, and you're not going to use the subset symbol. That's the second misuse of the notation there. So that's just something I wanted to clarify because people do commonly use the wrong symbol, and what they're trying to say is not matching up with what they are actually writing out. So here I just have a couple. I have a sample here. The set B here, 1, 2, 3, 4, 5, 6, and 7. And I have 3 separate sets here, A1, A2, A3. And the question is for each of these A's, is it a subset of B? Is it a proper subset? First one contains the elements 1, 3, 4, 2, 7, 5, and 6. As we said, the order in which you write these things does not matter. So every guy that's in the set A1 also lies in set B. So yes, A1 is a subset of B here. Is A1 a proper subset? Is there some guy that's in the set B that is not in here? Well, no, that's not true. Every guy that's in here is also in here. So what we would say is that A1 and B here are equal. So A1 is not a proper subset, but it is a subset. Continuing on with A2, A2 contains the elements 3, 7, 9, 1, and 5. Well, for A2 to be a subset of B, every guy that's in here would have to be in here. But here we have the number 9. There's no number 9 showing up here. So A2 is not even a subset of B. And if it's not a subset, then it can't be a proper subset. And then here, A3 is just the set containing 2. Every guy that's in this set, and there's only one guy, does also show up in the set B. So we know that A3 is a subset of B. And then also, is there a guy in B that's not in here? Well, yeah, we have several options. 3, 4, 6, several more options. So yes, A3 is not only a subset of B, but it's also a proper subset. So those are just the three sort of cases that you can have when it comes to two sets being related to each other. And something that you may be a lot more familiar with, the use of Venn diagrams to talk about sets. Here we have a little circle A inside of a larger circle that represents set B. Obviously, everything that's in the small circle is also inside that large circle. So A is a subset of B, and we have some space between the small circle and the large circle, so A is a proper subset. Here, we have the same circle. These two circles overlap perfectly. That's when A and B would be the same set. And then here we have two circles, typically like you see a Venn diagram. We see that these circles don't perfectly overlap each other, and also one is not entirely contained in the other. So there are guys in A that are not in B, which says that A is not a subset of B. We've mentioned some special domains earlier on in the course: the set of all natural numbers, the set of all integers, the set of all rationals, and the set of all reals. But how do these sets relate to each other? Well, these guys are actually subsets of each other. Natural numbers, the set of all numbers that are, the set of all whole numbers that are positive. So that is a subset of just all whole numbers, which is Z. So again, N, the set of all positive whole numbers, is a subset of just all whole numbers, which is Z. Every integer is a rational number, but there are rational numbers that are not whole numbers. So Z is a subset of Q. That's a special symbol that we use to stand for the set of all rationals. And then just the rationals make up half, in quotes, half of the set of all reals. We also have the irrational numbers, and the rationals combined with the irrationals make up all real numbers. So Q is a subset of R. So this is just a nice little visual to see how these four common domains that we work with in higher level math courses, here's how all those things tie into each other. So this was the first part of our intro into sets and how sets relate to each other, and how these guys can work. In the next video, we'll continue on with this. We'll see other relationships between two sets and see how we can come up with more sets from those guys. If you have any questions or comments, be sure to drop them in the comments section below. Otherwise, until the next video, take it easy, guys.